Hi, I'm Darren and welcome to Level Up Double E Lab. Today I'm starting a new project where I'm going to take some parts from my junk box and see if I can make something useful from them. So let's get started. When I was testing my new RF preamp design for my HF transmitter, I really wanted to make IMD measurements and compare the results to my older preamp design. I found a way to get some rough readings on the full transmitter chain by using a two-tone audio generator and my AirSpy HF SDR, but to check the IMD on just the preamp, I really need a different setup, and that begins with using two RF signal generators. Unfortunately, I have only one, my HP8657A, which is not turned on right now because the cooling fan is so loud it would drown out my voice. But I suppose I could go online and find another used one or a modern equivalent, but instead I'm going to challenge myself here. I'm going to build my own RF signal generator specifically for use for IMD testing. Once again, I've turned to my trusty copy of EMRFD for guidance. And right here on pages 7.18 through 21, you can find a detailed description of a fixed frequency crystal-based RF source that is suitable for making IMD measurements on receivers and transmitters. Perfect. This looks like it'll work just fine for my needs. Before diving right into the schematic, I've made this simple block diagram to show the basic function. The signal path starts with a crystal-controlled oscillator, which then feeds a differential amplifier. Next, we have a low-pass filter, then an attenuator before reaching a common base output amplifier. The net result is a 1 milliwatt or 0 dBm output signal. 0 dBm is more than sufficient for testing receivers, especially when you consider that you'd be using a lot of attenuation before feeding that signal into a combiner. But for testing RF amps, more signal strength would be nice, so that section in EMRFD also describes a 22 dB amplifier along with input and output attenuators to end up with a 10 milliwatt or plus 10 dBm signal. I'm going to build both the main stage and the booster amp portions, so let's switch over now to the schematic to see how they're constructed. The book version is designed around a 14 MHz crystal. Now, I might end up building two of these units, and if I do, I'll need two crystals very close to each other. 2 kHz would be ideal, but up to 20 kHz would be okay. I happen to have a bunch of older 40 meter crystals in my collection, and some of those are very closely spaced, so I've modified the EMRFD design to work at 7 MHz instead of 14 MHz. Okay, so the action begins over here with Q1. All of the stuff around it makes up a Butler oscillator, which is a version of the classic Colpitts oscillator. And here's my first change. I've modified transformer T1. I've added turns to the primary to raise the inductance, which drops the tank resonant frequency to match the middle of the 40 meter band. And doing so meant that I also had to add turns to the secondary to maintain approximately the same turns ratio as the original design. Resistor R6 sets the secondary impedance at 100 ohms, and T1 makes that look like about 10 times that on Q1's collector, which puts a light load on the oscillator. Q2 and Q3 are a long-tailed pair differential amplifier, no mods needed here, and then next comes a simple third-order low-pass filter. Now this definitely needs modification, and interestingly enough though, the caps and inductor in the book design do not match the typical Butterworth or Chebyshev table values. I suspect it's actually an ultra-spherical design. More on that when I get to some simulations. Next in the signal path is a 6 dB pad, which is there likely to help with impedance matching. And then lastly, we have a common base amplifier. The book says it's chosen for good reverse isolation, which is clearly something you need when mixing signals for IMD testing. And here's another change I made. I'm going with the surface mount DXT2222A transistor. The book version uses a 2N5109, which were ubiquitous 20 years ago, but nowadays they're obsolete and scarce, so I'm leveraging the work that I did recently on my RF amp evaluations and my HF transmitter project to select this guy. There's more detail in the book about these stages, and if you're curious to know more, well, you're going to have to go read the book. And also go to Wes Hayward's website to get the list of errata. The circuit shown in my edition did have some mistakes. I'll save the walkthrough of the booster amp for later. Right now, I want to dump out my crystal collection and root through it to find a pair of crystals that I can use. Here's what I have to work with. I've got several 100 megahertz crystals left over from my spectrum analyzer project. Those are not going to work. I've got this whole bag of 12 megahertz crystals that I picked up for an unbelievable deal at a Hamfest a few years ago. They are still waiting for their ideal project. 12 megahertz isn't that convenient, and it's not going to work here either, so I guess those will still be waiting. But the majority of my collection here I inherited from my dad. I got lots of these vintage FT243 crystals, even a few that are in an older package. I'm not even sure what style package this is, but I'm pretty sure it predates the FT243. These are very useful with the Viking Adventure transmitter that I showed a while back, the Hallicrafters HT40 and the Heathkit DX60. They all will work off plug-in crystals to drive their oscillator frequency for transmission. In this collection, I have quite a few that are on the 40 meter band. My dad was able to make these, or quite a few of these rather, work on the second and third and fourth harmonics with that Viking Adventure, and he even labeled on these at what frequency he was able to get them to oscillate. But I'm only interested in the fundamental frequency. I don't need the added challenge of trying to get a higher order frequency to oscillate here. I'm not sure at this point if I'm going to build one or two of these generators. If I build a pair, then I won't need to drag out that bulky HP SIGGEN, but I will be constrained, of course, by whatever frequency separation I have with a pair of crystals. 2 kilohertz is a standard apparently for narrow band testing, and up to 20 kilohertz is used for wider testing. But whatever I choose, I want the IMD products to stay within the band. And as it turns out, I've got this pair right here. This I was about to say TI, but that's Texas Crystals is the logo on there. Hopefully that comes through. 7.13 megahertz, or 7,130 kilocycles, as they used to call it. And the second one is from JAN, or JAN. It's 7.149 megahertz. Now, these will work. These frequencies, I should say, would work because even the ninth order products will still be in band. Some of the ones I have here are closer in frequency, but they don't use the same package, and I'd really like to keep the package the same between them if I'm going to build a pair of them. First thing I did was test them on my very simple crystal tester that I built. That is the exact same design that Alan shows on his W2 AEW channel. I built this a couple of years ago, and it's useful for just plugging it in, and yep, the crystal oscillates. That's definitely not a sine wave, but that's not important. We just want to see that the crystals work and that they work on their target frequency, and both do. So that's a good start. The next measurements I want to make here will collect data that will enable me to try to do an LT spice simulation of that circuit. So one of the parameters is package capacitance, or C sub P. I can measure that on an LCR. Just put the connections across there at low enough frequency, and you get a value in picofarads. No big deal. The other parameters, though, are a little more challenging. I want to know the series and parallel resonant frequencies, and there's a bunch of motional parameters that I want to know. But I can use the Nano VNA to make those measurements, and I have got this set up to do so. I made a simple test fixture here out of an octal socket because these crystals will plug right into an octal socket. In fact, that's exactly what's on the front panel of the Viking Adventurer for the crystal to plug into, and you can see I've got a profile there. And of course, I did calibrate the fixture using just a jumper for the through measurement before I make these measurements. I could try to pick the values off on the screen, but as always, using the Nano VNA Saver software is a better idea because, among other things, you can set a series of scans at finer resolutions, which is what I'm going to do next to get those motional parameters. And here are the parameters that I gleaned from the Nano VNA Saver software and the plus 45 and minus 45 degree phase shift analysis. Then plugging those into the standard formulas, that yields these motional parameters. That gives me what I need to set up a simulation of the oscillator portion of the circuit, and here's what that looks like. This network here is where those calculated crystal parameters go. L1 and L2 come from the 20 turns on the primary and 6 turns on the secondary. And C4 is the trimmer cap, used to set the tank resonance for reliable startup. And speaking of startup, I just can't get the simulation to reach steady state oscillation. I get a little bit of wiggle at the beginning, but that's because I'm starting L1 with a bit of current and using the startup parameter, both of which should kickstart the oscillator. But no dice. I've played around with so many parameters, including tweaking C4 around the series resonant frequency, but all for naught. The circuit just acts like it's overdamped. But when I replace the crystal with just 24 ohms of resistance, which is equal to the motional resistance, bingo, I get startup and steady oscillation. This is a well-known technique to tune a Butler oscillator, and it shows that the circuit is fine. There just must be something not quite right with my crystal model. Anyway, I'm done with tinkering with this model. It's time to move on. Next up is the low-pass filter. Let's see if I have better luck with it. For starters, the values of the inductor and the caps don't match the standard calculations for a third-order Butterworth or 0.1 dB Chebyshev. But nevertheless, its performance in the stop band is better than both of them, with very little ripple in the pass band. My best guess is it's a version of the ultraspherical filter described in Chapter 3 of the book. Unfortunately, there's no third-order table for those in the book, just a table for fifth order. But I was able to back calculate some values from the book design, and I extrapolated them to come up with my own version for 7 MHz. Here's how it compares to the original. Both filters have negligible losses in the passband, and both have similar attenuation values at their respective harmonic frequency multiples. So that looks like a winner. Oh, and just for kicks, I took a look at the input impedance. Looks like mine is very close to the book version. Both are just under 50 ohms at the intended use frequencies with almost zero phase angle. You gotta love an almost purely resistive impedance match. At this point, I could have continued with simulations of the differential amp and the common bass amp, but instead I decided to breadboard the circuit, and here it is. And it works. Ta-da! Look at that output on the scope in the background. So it's actually putting out around 270 millivolts RMS into this 50 ohm resistor, which is 1.5 milliwatts or about 1.6 dBm. And I can reduce it if I want to by dialing down RV1 right here and dialing it back up so I can fine tune, fairly precisely what output power that I want. For C4, I'm using this very large air variable cap that I pulled from the junk box, and this is just for breadboarding. It let me adjust the value to find kind of the center of stability, and once I did that, I powered down the circuit, disconnected the cap, and measured it, and it was right around 200 picofarads. So I used that data to set the values for C19 and C4 on my schematic. Those two are in parallel, so they add. C19 is a fixed 150 puff, and C4 is a trimmer with a range of 23 to 100 picofarads. I've also tested the circuit with a 2N5109 in place of the DXT2222A, and with everything else set the same, it gave slightly more output power, around 2.2 dBm. And I made these cute little adapters. Here's the 2N5109 in its, along with a little ferrite bead there to help suppress higher frequency oscillations. I'm just able to plug and play, swap these in and out, and not have to worry so much about the delicate leads on these devices. One additional check I did was to feed the output into my tiny SA through a 6 dB attenuator so that I could look at the signal cleanliness between the two transistors, and good news, they look almost identical. The highest peak is the third order one, and it's about 37 dBc, and that kind of makes sense. This common base design is not being driven that hard at all. It's staying comfortably in the active region, so would not expect a lot of distortion anyway. But the bottom line is this is good news. It looks like my modified design is acceptable. Next up, we'll be laying out the design to scale in KiCad, designing the circuit board, getting the board fabricated, and then populating it and stuffing it inside one of these cases. Now, these are interesting. These are some cases that I salvaged from an old piece of audio test gear, and I think they're going to work perfectly for these RF signal generators. They're just the right size. They're obviously going to be well shielded, and that'll be great for protecting them from any outside RF energy getting in, and of course any energy leaking out. So that, along with the design of that booster amp, will all be subjects for the next episode. As always, I hope you guys are enjoying the content here on my channel. So until next time, bye for now.